This video illustrates weightlifter, a novel technique for multi-criteria decision-making using additive weighting. The main goal of weightlifter is to increase the efficiency of decision-making and the certainty in the decision by analyzing the space of possible weightings, called weight space. It consists of three linked views: a visualization of the weight space, a ranked list of possible decision candidates, and a parallel coordinate plot providing an overview of the criteria, with the currently best ranking solution being mapped to a straight line. We illustrate weightlifter by a usage scenario where we want to decide which used Toyota Corolla car to buy. The decision is based on 6 criteria: price, age, guarantee period, mileage, quarterly tax, and the number of doors. Each decision criterion is scaled by a cost function that is displayed on top of the ranked list. Cost functions can be thought of mapping the raw values of the criteria to a common scale that represents objective satisfaction, with 0 corresponding to perfect satisfaction. In the linear cost function of age, for example, a new car maps to a cost value of 0, while a car that is 80 months old maps to 1. The costs of the criteria are weighted and summed up to attain overall costs that are used for ranking the candidates. The list shows a ranking of cars for the current weighting. We start with an equal distribution of weights. The top candidate in the ranking has the lowest overall cost based on the current weighting, and the color indicates that its cost originates only from its high price. Instead of showing all cars, the list only contains those cars for which a weighting exists that makes them rank first. This reduces the list to 24 cars. For each car, the column rank frequency shows the percentage of the weight space where that particular car ranks first. This information could be interpreted as a notion of importance. The remaining cars, which do not rank first for any combination of weights, are collapsed into a single row, and their distribution of costs is visualized as a histogram. The overall length of the stacked bars corresponds to the current weight, which can be modified by the user. Changing of weights can result in changes of the order. If we increase the weight on the price and the quarterly tax, linear Terra has the lowest cost and ranks first. As we can see from the distribution of its cost, it is a lot cheaper than the other model that ranked first previously, but it is also older and has a shorter guarantee period. A novel visualization of the weight space shows how the first ranked car ranks at other weight combinations. We can change the weight along any of the trade-offs by dragging the slider. The fifth visualization, for example, shows the trade-off between price and all remaining criteria. If we move the slider all the way to the top, 100% of the weight is put on the price. The left part indicates at which weights the best ranking car would change. We can now see that the best ranking car would switch to a Corolla 1.8D if we put more than 50% of the weight on price, and that a Corolla 1.8D station wagon would rank first if we further increase the weight to 60%. The blue histogram in the middle of the trade-off shows for how many possible combinations of weights this car ranks best. If we put about 45% weight on price, only around 1/3 of any combinations of the remaining criteria results in the same car ranking first. Two-way trade-offs can be added or removed by the user. The endpoints of the trade-offs can be defined by dragging the criteria to the endpoints of the visualization, or removed by middle-clicking on them. We can now directly inspect the trade-off between the criteria, age, and mileage. Moving the weighting along this trade-off thus affects only 2 criteria and does not change the weights of the other 4 criteria. A stacked bar on top indicates the sum of weights that is affected by the trade-off visualization. In this case, the length of the white bar corresponds to the sum of the weights for age and mileage. To recognize trade-offs that affect the same part of the weighting, trade-offs that are defined on the same criteria are shown connected. As our new trade-off only affects the weight of 2 of the criteria, the line connecting it to the other 2-way trade-offs is interrupted. Filters enable to exclude irrelevant parts of the weight space. For example, the price of a car could be considered important enough to ensure that it is weighted by at least 50%. This removes all cars from the list that only rank first when the weight on price is low. In addition to the 2-way trade-off visualizations, we also provide a visualization for evaluating 3-way weight combinations. Here we see a trade-off between the guarantee period, the age, and the number of doors. By dragging criteria to the corners, we can again change the displayed trade-off. We can distribute the weight among the assigned criteria by dragging the barycentric coordinate point within the triangle. Moving the point to the center puts equal weight on the 3 criteria that are mapped to the corners. Moving the point to one corner puts full weight on the criteria of that corner. For some decision-making problems, also solutions ranking second or third may be interesting. The user can specify the number of ranks that are additionally shown as context. We encode this rank context with a decreased brightness. For example, this reveals a car that often ranks well, but rarely ranks first. This concludes our demonstration of Weightlifter, a novel technique for multi-criterion decision-making. Thanks for watching our video.